So let's look over these together. For 1, 2, 3, 4, 5, any questions with those expansions? Maybe I should make this a little bit bigger. Oh, that means I have to restart. No, I will not make it a little bit bigger, sorry. Because I'm recording in this red box and I don't want to add on stuff here. We're good with those? So then, as we look down, for number 6, we're asked to fill in the blanks the coefficients of each expansion. So I'm just going to pull things out a little bit here. I'm going to look at the coefficients, and that's a good color. I'm going to make this a little bit wider. That's good. So here my coefficient is 1, and then I have a 1 and a 1. And then I have a 1, a 2, and a 1. Oh, noticing anything? A 1, a 3, and a 1. The next one, it's down below, but I'm going to put it up here. A 1, a 4, a 6, a 4, and a 1. Look familiar? Question? Yeah, so rearranging it breaks the pattern. So we're going to talk about how we'll arrange it to be able to see this pattern. And I guess we could start looking at it now. If I look at my first variable is a, and so I go in descending powers of a. I have a to the 4th, a cubed, a squared, a to the 1, and then this would have an a to the 0. So the first term that's in my binomial, I would go in descending order of its powers. And then for the second term, the b, I'm going to go in ascending order. So here this one actually has a b to the 0, which is 1, and then a b to the 1, a b squared, b cubed, b to the 4th. So that's the order that we're going to typically put things in, so that if we're asked for what's the third term in this expansion, we're assuming this order. Okay, so that's going to be important. But what we saw in the red up there is the beginning of Pascal's triangle, right? So when you fill those in, you've got these numbers, the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Scott. That's right. So the first term in the binomial will be descending. The second term in the binomial, the exponents will be ascending. So this looks like Pascal's triangle. So if I wanted to do the expansion, I could expand Pascal's triangle, or I could just think about, combinations. I could do some combination calculations. So what I found is, for this last one, where I had a plus b to the exponent 4, these are the coefficients from a plus b to the exponent 4. And notice this exponent of 4 is my n value in all of my combination calculations. And I'll start with n choose 0, n choose 1, n choose 2, n choose 3, n choose 4. Okay. So suppose we want to expand this binomial. So it's not as simple as a plus b to the exponent 4. Now we have 2x squared minus 3 all to the exponent 4. But what we can do is we can just say our a value is going to be 2x squared. So in our previous expansion, I had a to the 4th, so that'll be a 2x squared to the 4th. And then I go in descending powers of a. So the next one that's cubed, this will be 2x squared cubed. And this one will be 2x squared squared. 2x squared, and then the last one won't have any a's. It would be a 2x squared in brackets all to the exponent 0, which is 1. So that's the first part. And then as I look at the b values, notice I'm taking the sign with it, because my expansion was for a plus b. Since I have a minus 3, that negative sign needs to stick as part of my b value. So here I'll have a negative b squared, negative b cubed, and negative b to the fourth. And then I would do some simplifying. Yes. Yeah, if we wanted to expand a binomial, suppose I had, well, let's go with this, 2x squared minus 3 to the exponent 6. Rather than actually having to multiply all those binomials together, I could use this pattern to come up with the expansion quickly. Yep. So let's simplify this. Remember this 2 is in brackets to the exponent 4. So I do have a 2 to the fourth, which gives me 16 as my first coefficient. X squared to the fourth, a power raised to an exponent, we multiply those exponents. So that'll be x to the 8th. So again, remember, we had a 2x squared times 2x squared times 2x squared times 2x squared. So just to review those rules, I have a 2 times 2 times 2 times 2. Oh, that's 2 to the fourth, which is 16. And I have an x squared times x squared times x squared times x squared. In total, I end up with 8 x's being multiplied together. So that's where that first term came from. Question? That's an excellent question. Why did I do that? Oh, because I wasn't thinking really clearly. I guess I'll have to give you a candy. I'll have to erase those and turn them into 3's. Thank you for pointing that out. Yes, that should be a minus 3 for each of those. Saad, do you have another mistake to point out? Thank you. I don't know if I could take it. Uh-huh. Yep. Yeah, so the secret was that since this exponent is 4, that tells me I'm starting my first term. There my coefficient was 4 choose 0. And then here I had 4 choose 1. And then there I had 4 choose 2. And then 4 choose 3. And then 4 choose 4. So those were the coefficients, in addition to the coefficient that I'm going to get from this 2 being expanded out. So in my final expansion, those aren't the numbers I'm going to see, but they are part of my calculating to figure out what those coefficients will be. Oh, because I start with my a to the fourth, b to the 0. So negative 3 to the 0 is just 1. So that term doesn't show up here. We're good up till there. Okay, next I have the 4 times 2 cubed is 8. X squared cubed is x to the 6th times the negative 3. And then 6. X squared squared will be a 4x to the 4th. Negative 3 squared is 9. And 4 times 2x squared times negative 27 plus 81. So you might have expanded this more quickly, doing it on your calculator or something. Doing it in my head is a little slower. 16x to the 8th. And then negative 12, so 4 times negative 3 times 8 is, I have a number coming to mind, but I don't know if it's right. Is it 216? No. The next one's 216 then. I know there's a 216 in here somewhere. 8 times 12, 96, negative 96, x to the 6th. Yes, the next one, plus 216 x to the 4th. I think the next one too is a 216. This one should be a minus. So there's my binomial expansion. So binomial tells me I started with a term plus or minus another term in brackets to some exponent. So when I say binomial expansion, it just means I've taken this thing and I've multiplied all those factors together, but I've taken a shortcut to come up with this expanded version of that polynomial. Rabia. Yeah. Initially I thought back to this line here. And I said, oh, I know what a plus b to the 4th is. So since I already had this expansion here, I just replaced all the a's with a 2x squared, and I replaced all the b's with a negative 3. So normally I wouldn't have done this part already, but this would be the process. So I would start setting it up, kind of doing the expansion like this, and then I do a substitution in. Yes? Well, I think we'll do an example yet. And so I would typically take a shortcut. So I would have, well, let's see if there's an example that'll come up, and then we'll look at it. So any questions with number 7? We're good? Okay. Here is a scary looking expression. So we're going to break it down into small pieces. So, oh, it's not that bad. So we're going to start with looking just at the coefficients. What you see in the coefficients, notice in my binomial, I have this exponent of n. So in all my combination calculations, I have n choose 0, n choose 1, choose 2, and then it's going to continue on until I get n choose n. So the question we just did, we started with a 4 choose 0, then we did 4 choose 1, 4 choose 2, 4 choose 3, and we stop at 4 choose 4. So when my r value equals my n value, that's when we stop. Which, by the way, tells us in our expansion, since my exponent here is a 4, and I start with 4 choose 0, I actually end up with 2, 3, 4, 5 terms. So there's another pattern for us to observe. If the exponent, whatever the exponent is for our binomial, the expansion will have one more term than that exponent number. So here exponent was 4, we ended up with 5 terms. Okay, so there are the coefficients. That's the first part of what we're looking at. Next. If you look at the x's, so the x, that relates to the first term in the binomial. And as we mentioned before, I start with the same exponent here that my binomial had. So since my binomial was an exponent n, I have x to the n, and then I decrease by 1 every time. N minus 1, n minus 2, continuing down until I get to 1 and then to 0. Good with that? And then if we look at the y's, so y's, second term in the binomial, it starts with a y to the 0 and then increases by 1 every time. 1, 2, and then all the way up until we get to n. Okay, so that's the order that we are always considering our terms to be in. And so, again, sometimes we'll have a question that says, what's the 7th term in this binomial expansion? We're assuming this order. Okay, so it's important that we recognize the order of the terms. Any questions with that whole long expansion up here? It's odd. Y2, oh, over, we're talking about to get from here to there. There's a bunch of stuff in between that we can't specify because we're using generic terms like the n in the exponent. We don't know how many terms there are there unless we know this n value. Other questions? Yes. Typically, yes. There could be variations where you're given a term and you need to work backwards to figure out what is that n value. So let's look at some sample questions. Oh, but first, the general term. So your workbook, textbook, gives you a different general term than what I've given you here. This is the term as you're given it on your formula sheet from Alberta Ed, so this is the one that I will use. Okay, your textbook will do it slightly differently. There's also works, it's just which formula do we want to use. So this is saying term k plus 1, which seems like an odd way to say it. Like if I wanted the 7th term, then I'm going to think, oh, my k is actually a 6. So my k value is 1 less. The reason for that is to make the numbers simpler on the right-hand side. I think what your work text does is it maybe has a subscript here of k or some other letter, and then has different variables in the exponents. We'll go with this one. So if k is 0, that would give me the first term because I would have 0 plus 1. Oh, that would be term 1 in my expansion. Similarly, if k was 1, would give me the second term. K2 gives me the third term. Let's just use this in a question and then talk about it as we do it. So we're not going to use that for number 8. Oh, yes, we will. We want to find the third term. There we go. I want to know term 3. Because I have this formula, term k plus 1, I'm going to turn this into a term 2 plus 1. Why? Because that tells me that my k value must then equal 2. Once I have my k value, then I can use this formula. As I guess I don't want to scroll down too much yet. As I look at my binomial, the exponent is 4, so that tells me my n value is equal to 4. So I have nck. I know my n value is 4, so I have 4, choose 2. That's going to be part of my coefficient. And then I have x to the n minus k. N is 4, k is 2. And I have y to the k, so my k is 2. And then I want to think, this is the first term. So in our warm-up questions, we used a and b. In this formula, they use x and y. So that whole thing represents my x, so this is my 2x squared. Is that color okay to see in the back? Anybody got a problem? We're okay? And then similarly, that -3 will be my y value if I'm thinking x plus y. So I have the negative 3 in place of the y value. So Krishna, earlier you asked, do we stick in the a's and the b's here? No, we can already do the substitution of what they're equivalent to in this expansion. So x gets replaced with 2x squared, y with a negative 3. That's good. And then we just simplify this. So 4 choose 2. We evaluate that on our calculator. I think it's a 6. And then I have 2x squared to the 4 minus 2, which is squared. So 2 squared is 4. X squared squared is x to the 4th. And negative 3 squared is 9. So 216 x to the 4th. That should be term 3 in my expansion. So let me just scroll up for a second. I'll come down again in a moment. And I'll look at my expansion. There's term 1, term 2, term 3. Yep, a positive 216 x to the 4th. So that's giving me that third term. Any questions with that example? Praveen? They will not ask you to find a term that's non-existing. They could ask you, is this a term in this expansion? So it could do that, but they won't lead you on to try to find something that doesn't exist. Chef. Yeah, you could do the expansion stuff. Yep. And often what I will do with questions is rather than doing a calculation like 4 choose 2, I'll do the expansion of Pascal's triangle because it's fast. So I might do 1, 1, 2, 1, 1, 3, 3, 1, 1, 4. So again, this tells me my n value was 4, so I'm at the right row. 6, 4, 1. Oh, and then I want to use that 6. So I might do an expansion like that because it's quicker sometimes than actually doing the combination calculation. Saad. That's right. So that's a good question for us to talk about right now. When we think about the expansions, this is like x plus y to the exponent 0 is going to be that first row. Anything to the exponent 0 is 1, so it's just equal to 1. The next one is going to be x plus y to the exponent 1. That'll be in the second row. So again, our n value is always 1 less than the row number. The next row, this would come from x plus y to the exponent 2. And again, it's that second term that matches with that n value of the exponent. So this one, x plus y to the exponent 4, and my second term is a 4. Because that's 4 choose 1. Starts with 4 choose 0, which is always 1. My second term will match with that n value. Good. Okay. We want to find the middle term in this expansion. So middle term in the expansion. Here's where I'd probably make use of Pascal's triangle to help me out. So I'd say, well, I'm going to start building Pascal's triangle until I get my second term being a 6. So we'll do 1, 1, 1. So this would be the row that I'm interested in. My second term is a 6. I want the middle term, so I can think, oh, this is 6 choose 0, 6 choose 1, 6 choose 2. This will be 6 choose 3 is where that 20 will have come from. So if I think of my formula, tk plus 1 is equal to nck x to the exponent n minus k y to the exponent k. So this is on your formula sheet, so you don't have to memorize it. So then since I know that that's the term that I want, that reminds me that my n value is 6, which I already knew from that exponent. But it also tells me my k value must be a 3, which simplifies things down for me, and then I can just start putting things into the formula. Rabia. Because my second term is always n choose 1, which is equal to n. So since I wanted my n value to be a 6, my second term matches my n value. So let's substitute in here. 6 choose 3. 6 minus 3 is 3. And then k is also 3. My first term, 3m squared. And my second term is a positive 4n. And then we'll just expand and simplify. Pauline? The exponents for x and y, if you're looking for the middle term, yes. So now that we've seen that, we could have avoided all this work, and we could have said, oh, since my exponent here was a 6, half of that is a 3, so I would need to have a 3 here and a 3 there. So once we do a few questions, we start finding more patterns. But if we didn't know that, then setting up the triangle helps us. Or if we forget, the triangle will help us. That's good? Okay, let's evaluate this. We know 6c3 is 20. 3 cubed is 27. M to the 6th. And then 4 cubed, 64. M cubed. And we get a number too big for my brain. 34,560 m to the 6th n cubed. That what other people got as you worked it out? Yeah. Okay, now notice, even though as we originally set this up, we had, let's go with this. Those two exponents were both 3's, so they were equal to each other. But once we did our expansion, notice the m and the n don't have equal exponents. Because in our original setup, I had an m squared, not just an m. So be careful not to make assumptions in your final answer saying, oh, my m and n have to have the same exponent, so what term will have that? We need to think about all the other little details that impact the exponents we'll get in the end. Saad. If my n value was odd, then it could not have asked me for the center term or the middle term. So you won't be asked that in that situation. Yes? Yep. It's not so much the number of places, but it's the R value. Go away. So I remember that I always start with choosing 0. Then I choose 1, choose 2, and found my middle value was choose 3. And that, then I compared back to this and said, oh, so I have a 6, choose 3, and is 6, k is 3. It's not the amount of rows, because this is, so there's row 1, 2, 3, 4, 5, 6, 7. So this is actually row 7. Yeah, but it's the second term matching the exponent that I had up there. Does that answer your question? Okay. Yes. Yep. Nope. Just for the numbers that we happen to have in that question. So what he was referring to was the fact that we have a 216 here and a negative 216 there. And should we expect to see a pattern like that? And the answer is no. Sometimes it happens, sometimes it doesn't. It all depends on what these terms are that are in our binomial to begin with. Okay. One more example. One term in this expansion is that negative 19,000 stuff, x to the 5th. We want to find a in this expansion. I'm going to give you a couple minutes. What do you think you should do with this? Feel free to ask a neighbor and help each other out with it. Just before we go over that question together, there's one more thing I wanted to point out, another pattern in the expansions. And that is here, for example, if in my binomial, both of these terms have an exponent of 1, then the sum of the terms, I should say the sum of the exponents in each term has to equal n. So there I have a 4, there I have a 3 and a 1, oh, that adds to 4. Here I have a 2 and a 2, that adds to 4. Here I have a 1 and a 3, adds to 4, and that one's 4. But as soon as we have a question like this one that has so much writing on it already, but kind of since this is squared and the next one doesn't have any variables, that doesn't happen in my exponents in the same way. Okay, in my final answer. It's still part of the pattern along the way. So here I had the 4, the 3, and the 1, the 2 and the 2, the 1 and the 3, and then the 4. So along the way that pattern's always happening, but it may not show up in the very final answer. Okay, now on to this question. A variety of ways we could start, but what I did was I wrote out the formula. I already knew my n value because of that 8. My n was equal to 8. So I filled that into the formula. But then as I compare the two sides, that's the only term that has an x, and there's my x. So since my left, or I should say my right side has an x to the 5th, my left side must also have an x to the exponent 5th, which means x to the 8 minus k must equal x to the 5th, so 8 minus k equals 5, and my k value must be 3. If you had a question like this on a test or quiz, I want to see, and you're asked to algebraically determine, remember determine means show process, you should show me where you're getting your k value from. Many of you will be able to, with practice, just look and see, oh, I know this must be the k. But on a test or quiz, make sure you communicate clearly. So In the formula, yes. Yes. So something that maybe should have been stated in this question is that k is a real number, a whole number, an integer. So I should say, a is not a variable, a is a number in this question. And we want to figure out what is that number. So that should have been stated in the question, and hopefully I remember to look over the quiz to fix it if it's missing in a question. Yes, probably. Yeah, we could do Pascal's triangle here, and then I'd look to see, what am I looking for though? Well, because this is my first term, I think my first exponent is 8, and then 7, 6, 5. Yeah, so then I'd know which term I'm looking for in Pascal's triangle. I'll just continue this one this way. So I know my k value is 3. So I have 8 choose 3, x to the exponent 8 minus 3, a to the exponent 3, and this is equal to 19208 x to the 5th. Now what I would like to do at this point, students don't always like if I do it, which is ignore the variables. So I know that this is an x to the 5th, and this is an x to the 5th, so I really don't care about that on both sides. You could say I'm dividing it out, or you could just say I'm looking at the coefficients and I'm equating coefficients. So I'm going to say my left coefficient, which is 8 choose 3, which is 56. And if a is a number, a is going to be part of that coefficient. That's going to equal the right coefficient, negative 19,208. If you left the x to the 5th in, it's fine. It's all going to work out. But I'm just going to ignore it because it doesn't affect the numerical part that's being multiplied to it. So we'll do a bit of math here, dividing. And I get a cubed negative 343, which is since my left number is cubed, I could cube root both sides. On my calculator, I never find the cube root button fast enough, so I will always just do it to the exponent 1/3, because that's usually faster for me on my calculator, which gives me a equals negative 7. And there we go. Rabia. That was given to us in the question, the negative 19,280 or 208. That was there. Yes. Why there's... Yeah. So it's a math strategy which would say if I had something like that equals if I knew this equation was true, would I know what A is? Yeah, I just look for the matching, the like terms, and I equate their coefficients. If I know 2x squared equals ax squared, oh, A must equal 2. So what I'm doing is I'm just ignoring the variable because it's unnecessary for me to figure out the answer. And here I could figure, oh, my B value must be a negative 3. My C value must be a 4. So I'm just making comparisons between two sides of the equation. So that's what I did here. Because at this point, both sides had an x to the fifth, I said, let me ignore the variables and just focus on the numerical part. So that's what I did. You don't have to do that. You're welcome to leave it in, but I think it's good for some of us to see that mathematical strategy. Yes? If the x value, yeah, if they had differing exponents, then I have a problem. Then there's no way the two sides can actually equal each other unless there's some other term that has a variable in it that I just didn't know about. Okay, I think there's one more question in your notes, right? Which looks like this. We're going to find the term where a and b have the same exponent. I'd kind of like to give you some time to try this, but we don't have a ton of time. I'm going to give you 2 minutes. See what kind of progress you can make in 2 minutes to get started. 2 minutes? There's not time for me to finish it. Oh, well, we'll see. I'll just get this one started. You may be done, but just in case. Anybody have a tip? What could I do? Yes. Yep. Yeah, so let me just do one more line. So since here I have a power raised to an exponent, I multiply those exponents. So I have b to the 2k. And if I know that a and b have the same exponent, that means 39 minus k must equal 2k. And then we'll use that to figure out the k value, and then we can finish the question. So there's a key to get started for this one. And we have 30 seconds till the bell. So I'll let you finish this. Compare your answer with your neighbors. And will I give you the answer? Oh, maybe someday, or maybe not. So tomorrow we'll have some time to work on review questions from the assignment that I gave you. Again, not for marks. And there are a couple diploma release questions we can look at sometime. So we have the next 2 days to review before Friday. Alrighty.